So in this video, guys, we're going to talk about tangent lines and derivatives. Now, a couple videos ago, a couple sections ago, we talked about this idea briefly of a slope predictor. And it was defined as the limit as h approaches 0 of f of x plus h minus f of x all over h. And that was our slope predictor in the sense that it gave us the slope of the tangent line to our curve at any given point. It was a formula of sorts that we would plug our number in. It would spit out then the slope. So that was our slope predictor. That also gave us our instantaneous rate of change at a particular point. Now, instead of calling it a slope predictor throughout the course, we're going to change things up a little bit, and this is now known as the derivative. A derivative is once again synonymous to the instantaneous rate of change at a point. And if you remember back from the very first video I put together, half of calculus is more or less all about instantaneous rate of change and the equation of the tangent line to a curve, which we found some of those before. And so for the derivative, the notation we'll use will look something like this. You can use things like f prime of x. You can use things like y prime of x. You can also use a dy over dx, so a dy dx. And again, this is just the same thing as the limit as h goes to 0 of f of x plus h minus f of x all over h. So the only real difference is going to be the context moving forward and allowing us to do some other things. So remember, this is really nothing different than what you've seen in the past. We're now calling it a derivative, and you'll see how it can be used in a couple different applications all throughout the course. So for our first example, we are actually going to find two different tangent lines on the curve y equals 4x minus x squared passing through the point 2, 5. Now, when I draw a picture here, if you can be exact, great. If you can't, most of the time it doesn't have to be perfect. So what I know is that my 4x minus x squared is a parabola that opens down. And I know that I'm looking for two tangent lines to come off of this passing through the point 2, 5. Now, the point 2, 5 is actually not a point on this graph. Okay, so 2, 5 might be sitting somewhere out here. And so our tangent lines then, one might look something like this, the other might look something like that. And those are the things that we're going to be finding. Okay, so maybe I'll put those in a different color so you can see them a little bit better. There's one of them, and there's the other one. So this is our point 2, 5, and you can certainly confirm that on your own if you need to. So remember, we're coming up with the equations of tangent lines, and if you need the equation of a line, you always need a point and a slope. The point is obvious, that's been given to us. So it's going to be all about these individual slopes. And so what I'm going to do is I'm going to go back to algebra. And in algebra, we know that the slope of a line is the change of y over the change of x. In other words, the difference of two y values over the difference of two x values. Well, I've already got one point. So my other point here, let's say that x coordinate is a. If that x coordinate is a, notice it's still on this curve. How would I find the y coordinate? Well, if x is a, to find the y coordinate on this curve, I would plug it into my function. So my other coordinate would be a 4a minus a squared. So now I've got 2 points. And again, I know that from algebra, the slope of that line can be found by using the change of y over the change of x. So if I take the change of y, that's going to be 4a minus a squared minus 5 over the change of x, which would be a minus 2. So that's going to be the slope of this line right here. But now I can also find the slope of this line by using the slope predictor or the derivative. So maybe over here to the side, I'm going to take the derivative of f, which is the limit as h approaches 0 of our 4x plus h minus x plus h quantity squared minus 4x minus x squared all over h. So once again, that's just our difference quotient with the limit out in front, providing us with the instantaneous rate of change, now calling it the derivative. Now, I'm not going to go all the way through this. You certainly could on your own. But when doing so, you would find out that once we evaluate as h goes to 0, you end up with a 4 minus 2x. So there's our derivative. If we want to know what the slope of that line is going to be at the point x equals a, we'll evaluate and we'll get a 4 minus 2a. So what we've just done now is we found this slope essentially two different ways, but they have to be the same slope. So this guy needs to be set equal to this guy. So I'll come back over here now in blue up top, and I'll set this equal to 4 minus 2a. Okay, so again, this is just finding the slope algebraically. This is finding the slope now using the derivative, but either way, they should be equal because they represent the same thing. So now it's just a little bit of algebra. And I'm going to kind of move through the algebraic steps a little fast here because I think most people can feel pretty comfortable with that. When you cross multiply there, you'll end up with, and multiply everything out, you'll end up with a 2a squared minus 8a plus 8 equals a squared minus 4a plus 5. I'll take that down one step further, and that'll give us a squared minus 4a plus 3, still set equal to 0, in which case now we can factor this thing into a minus 3 and a minus 1, so that a equals 3 and a equals 1. So earlier, when I focused all my attention on this guy, some people might have been thinking, well, why not this one over here? Well, remember, this is very general. I could have called this A, and I could have called this A for the x-coordinate, and then the y-coordinate would have been the same. So, but notice how I came up with two different answers. That's a good thing because that tells us there should be two different points on the curve where this is about to happen. So, if we know that A is equal to 3, now to find our actual slope, I'll come back to one of my forms. This is probably the easiest. If a equals 3, it looks like I'm going to get a negative 2 out of that. And if a equals 1, it looks like I'm going to get a positive 2 out of that. So remember, these are your slopes. There's one, and there's the other. We have our slopes. We have our point that's been given. So now, I'll box this out a little bit here. You're going to have y minus 5 equals a negative 2 times x minus 2, and you'll also have the y minus 5 equals a positive 2 times x minus 2. And when we simplify this down, we should get y equals negative 2x plus 9, and y equals a positive 2x plus 1. So these should be the two lines now that are tangent to this curve, but also run through this point. And if there was ever a problem to need to visually see and convince yourself what we did was correct, this was probably the one. So hop on to Desmos, graph this equation right here, this function. You can even plot this point in Desmos and then graph these two lines as well, and you should see a very similar picture to what I have drawn right here. So again, really nothing new in terms of what we've done. I did pick a more difficult problem because we're kind of past the monotony of just finding the equation of a tangent line to a curve. We can spice it up a little bit, but the only difference was now I'm referring to this instantaneous rate of change as our derivative, which is still providing us with that same information as before.